I want to say that um, tomorrow evening or maximum tomorrow morning, maximum tomorrow evening, I will publish the completely the exercise number 2, and I I invite you to see the content of the numerical exercise. You have to take. I'll give you any kind of support in terms of mathematical code and related issues. I present you completely the model, and you have to use this model for studying the elastic stability of the model in considering a set of parameters assigned. I have to find the flutter limit and frequency. However, please start to see the model, and next Monday in the afternoon, I present you in detail the theory that I announced this theory yesterday. I give you a very some and fast description of the continuation method for finding the flutter limit. And however, in the code I will provide to you, there are also the algorithm implemented for finding this limit. But I invite everybody to see what happens and to find this limit and do a very brief report on this exercise. The interesting thing is that after that, I will invite you to do the same exercise by using a commercial code, by using Nastran, the identical exercise. And this will allow to you to use Nastran code for this exercise, but in general, you will be able to use the code for any kind of wing. And this is the power of this kind of teaching procedure. I introduced to you the general theory. I introduced a theory in analytic case. We find with MATLAB the solution with the analytic case, but we can implement the solution for this elementary case with Nastran using the general theory, and so you will be able to use the general theory by commercial code. Okay, this is my teaching step for allowing all of you to invite all of you to use this kind of algorithm and procedures. Okay, we can start for the last part of our lesson. And okay, let me be clear with you, step by step. First step, we find the analytical formula for expressing the solid angle in stereoradiant here, able to measure the solid angle viewed by this point for observing this elementary surface. So you have an elementary surface, ds, so you have an elementary angle, solid angle, d omega. This d omega is related to the normal to the surface, the unit vector of the point of the vector, the unit vector associated to the vector defined by the x point and the x star point as difference between the x star point and the x point, x minus x star, excuse me. And that's all. Okay, so this angle, this solid angle, d omega, is the scalar product between m dot r by ds divided by r, the distance, to the power 3. Point, period. This is what we have found, okay? Okay. Now, a flashback. Let's add a flashback. The flashback is on the general theory of the panel method. In that general theory, we have a body surface and wake surface, and we have a formula connecting the velocity potential in the x star point, in fluid point, with the velocity potential on the body and on the wake by this formula. Okay? Okay. If you want to discretize this formula in space, you use a zeroth order approximation. So this means that any unknown and known quantity are assumed to be constant on a panel domain. You have this formula transforming your analytical integral formula, and you have some coefficient like B or C or F. In particular, C is the coefficient arising by this part of the problem. When you assume a zeroth order formulation, the term phi inside the integral of this panel is constant, so you can move this quantity outside the integral, and the integral, the remaining integral is this here. Is an integral located in a generic panel J, like this. And in order to evaluate this coefficient, we have to take the integral on this panel of the quantity dg on the n on the s. Okay? Period. I want to show you that this quantity is exactly this quantity. In other words, it's the angle you are currently seeing your panel by a point. Excuse me, this quantity is the omega, and therefore the integral on the panel is the finite solid angle you are seeing in the panel by this point. Okay, and I want to show this, and at the end I want to connect this point with the definition of the domain function. Okay, so please be strong and follow me. No, we are finished, don't worry. In particular, at this point, consider the quantity dg in the n by ds, exactly this quantity here. Okay, surrounded by red color. Okay, this quantity is equal to, what about dg in the n? dg in the n is the product between the normal and the gradient of g, the gradient of g in the s. But the gradient of g is the gradient of -1 divided by 4 pi r. Yes. Okay. Now, what about the gradient? The gradient of 1 on r quantity, this is the x star point, and this is the x point. If you have a field like this of type 1 on r, this gradient is 1 on r is a scalar function whose gradient has the direction of the radius, of course. So this gradient is equal to the unit vector er This is the direction of the gradient. And the entity, the amplitude of the gradient, is the derivative of, with respect to r, of -1 on 4 pi r. In other words, the natural coordinate for evaluating the gradient of -1 on r, the natural coordinates are the spheric coordinate, because the deep dependence of this scalar function is on r, and therefore if you want to determine the gradient, the very natural coordinate system for evaluating this gradient is the spheric coordinate system, not the Cartesian one at all. Okay, so this is the gradient, and therefore if you consider this quantity is ER, and the derivative is 1 plus 1 4 pi r to the power 2. Okay, and ER is equal to the vector r divided the amplitude of r. This is the unit vector, and therefore you have by 1 4 pi r2, and therefore the gradient is equal to the vector r by 1 on 4 pi to the r to the power 2. This is the gradient, and therefore the quantity under discussion is n by r n by r ds and divided by 4 pi r to the power excuse me, to the power 3, because we have r and r to the power 2. Okay, and so we have this r, excuse me, r to the, oh my god, oh excuse me, oh excuse me. Okay, but well, we have only to compare this with this. And therefore we have that dg on the n is equal to d omega, this is d omega, divided 4 pi and therefore the coefficient for here, for example, the coefficient ckj is representing the integral of d omega by 4 pi. So you have just to the integral of the omega on the panel Sj is the solid angle associated to the panel J when you see the panel from the point K. So you have omega from the point X star of the panel J divided by 4 pi. And this is a very interesting interpretation for the coefficient. In particular, One point could be the following. How many wake points I am obliged to consider in my discretization? Look, if you have problem with a wake, you have to decide in your linear, for example, discretization, how long consider your wake distribution. How many panels in the wake I have to consider? Theoretically, this wake is infinite. It starts by the airport and then is actually attached to our leading edge line here. However, how is important this panel? For example, this panel is a panel arising by this discretization. It's F. But F is identical to C. Yes, because again, you have a delta phi and you have the integral of the G on the end by the S. So this panel is the panel which is seen by this point on the wake. And so the contribution of this panel is given by this angle. I don't know if you this yellow angle, yellow. And therefore, if this panel is the N panel, and this is the, again, the K point, your Fkn is equal to the integral of, on the panel N, of the G in the N, the S, which is equal, and is equal to omega x kappa divided by 4 pi. Okay? And therefore, as long as this distance between the wake panel and the body, and lower and lower is the relevance and the value of this Fk contribution. So you can drop, you cannot consider the panel from wake length on. This is the wake length of wake. You can not consider this distance, this panel, from a reference value on. You mainly may consider a wake length in the calculation as equal to 4, 5, 6 times your chord length, okay, as a reference length. So this is equal to almost 10 chord length C. Interesting. And as a very last comment on this number 2 discussion of today, I want to introduce in a new way my domain function E star. What about E star? E star is a function defined as equal to 1 if x star is outside the body surface, is equal to 0 if x star is inside the body surface. This is the body surface, okay? And let's introduce star is equal to 1 minus omega x star divided by 4 pi, where omega x star is the finite, not infinitesimal, solid angle associated to the total body surface SB when it is viewed by the x star point. Example, this is our solid surface as body. When I'm inside here with my x star point, when my blue Spanish eye is here, what about the angle you see? The angle you see is the total body. Total body means that in this case, omega x star is equal to 4 pi. Because 4 pi is the value of the solid angle of the universe around me. All the spheres with unitary, all the sphere surface with unitary radius, 4 pi by the radius 1 to the power 2. So 4 pi. Okay? When you are outside with the x star point, and you try to see the surface, remember that you are viewing the white and the black side of the moon. So the black side of the moon has a negative contribution. The white side of the moon for you is as and gives a positive contribution, just opposite to the dark side. So in this case, omega x star is equal to 0. And so if you accept this definition for E, you have exactly the same effect. You have 1 minus 1 in the case of a point inside your moon, and your body. And whenever you are outside, you have omega equal to 0, and therefore 1 minus omega by 4 pi is giving you 0. But in this case, you are also able to see what happens in the case your x star is on a point surface. In the case of x star in the S body here, regular point means unique tangent. Tangent plane. In this case, when you are here, how do you see? What about your view of your surface? You may see half universe, okay? Because you are a point in trying to see a surface. And so you have omega, in this case, omega in x star is equal to 2 pi, half sphere. And Of course, you may imagine that if you don't have a regular point, for example, if your point is on the tip of a pyramid, for example, or on a tip of a cone, you have the value of the cone angle as solid result, of solid angle result. Okay, but in the case of regular point, you have 2 pi. And therefore, with this definition, you have this definition is able to generalize the role of the x star point for any kind of surface, for any kind of point, inside the surface, outside the surface, on the surface. Okay, on the surface. And remember that this value, omega x star divided by 4 pi is equal to the integral of our viewed surface, the body surface in this case, by dg in the n, ds. And therefore, look, if you apply this to definition, you may revisit our boundary integral expression. So revisit you can revisit the equation star, and then we have E is 1 minus the integral dg in the n ds by, this is E, by phi x star equal to, I am rewriting this question, and so we have equal to integral on the key g minus phi dg in the n. This integral is on the body, as body. Also this is on the body, ds minus integral on the wake, delta phi dg in the n, ds. Okay, and what does it mean? This integral can be moved in the right hand side here, and this integral is an integral depending on the x variable, not on the x star variable. So we can move this inside, and we can write here phi in the x star equal to, so 1 by x star is this, then we have minus this by phi star, and I can move this part in the right hand side, and so we have integral SB key G minus, look, phi the x minus phi in the x star dg in the n ds minus s wake delta phi dg in the n. In other words, I have moved this part here in the right hand side, and we can do this because this integral is an integral in the x variable, not in the x star variable. So phi in the x star value can be moved inside arbitrarily, with no problem. And we have moved inside, and we have moved all the integral in the right hand side. So writing this contribution plus this contribution, which is from the left hand side. And what is the advantage of this integral formula? This integral formula is independent on the nature of the x star point. We don't care if x star is on the surface, is inside, is outside. This is a general formula. It's a very general formula for boundary integral equation. So in some book you can find your integral equation in this form here, which is general, independently on the nature of the x star point. Or you may have a more detailed expression of your formula in this form here. But here you have to specify the value of E in the case x star is on the surface, is inside the fluid, is inside the body. Okay? Interesting. And now you know everything about the boundary element method. You are an expert. If you want, you may build a code. You may build a code for calculating the potential flow for unsteady and steady aerodynamic. Okay? Okay. I finished to introduce my number 2 item of today. Today we have explored this number 2 items, domain function. Here we have explored the number 1 item, meaning of Strom number or reduced frequency, and initially we have discussed the generalized aerodynamic force matrix as a frequency response matrix. And therefore we interpreted the result of this operator in frequency domain, considering the concept of steady state harmonic solution. Okay, now I want to now to consider another argument, interesting argument, and the argument is the following. The argument is the finite state approximation of the generalized aerodynamic force matrix E as a function of omega and u, or if you prefer, as a function of k. So this metric is also known as GAF or GAF in Italian. Okay. And what is the point? This kind of approximation has a double phase. It is a double phased problem. First phase, you have a term of this of this aerodynamic matrix as a function of k. So you may represent this real part of Eij and imaginary part of Eij as a function of k. So the real part could be something like this. The imaginary part, look, could be something like this. The imaginary part of any kind of transfer function is always starting by 0. At 0 frequency, you have 0 imaginary part, always. And you have a straight linear trend in the neighborhood of 0. And the real part is always something starting with 0 derivative, something horizontal here. This is a story which is common for any kind of transfer function. Call to expert people about system theories on that, and they can tell you a story about this. However, in the first phase aspect of this story, the point is the following. If you know this matrix infinite point like this, you know, this here, because you don't want to spend computational time on evaluating your matrix, so you want to evaluate your matrix only in a finite set of points. Okay, question. Could be convenient to have a matrix polynomial approximation of such a matrix, GAF. In other words, it could be convenient to have Aij kappa to be equal to an I0 Ij plus I1 Ij by jk to the power 1 plus I2 Ij by jk to the power 2 plus So this is a polynomial approximation of this data that could be evaluated by, for example, do you know the regression straight line? La retta di regressione o qualsiasi forma di interpolazione. If you know any interpolation form, you could evaluate this matrix coefficient. This is a product. You may evaluate this matrix coefficient, and you may consider this power on an other interpolating structure. So you may evaluate this coefficient by imposing that your fitting structure has a minimum distance with respect to the data assigned. Okay? Question for you. Does this approximating form make sense for this kind of matrix? Or not? We know that in deep aerodynamic matrix, look. What is it? We did. Okay, we know that the aerodynamics matrix, the overall aerodynamics matrix, is depending on P, 3 times, and these 2 times are depending on linearly on P, and this here is depending exponentially with P. So we know that we have this kind of dependency. So if you want to fit our data, the bullet are evaluation of E by computer. And then the black line is an interpolation. May I find this interpolation assuming an interpolating structure of this type? Yes, we can. Okay. And this is one phase of the medal. To see this point as a polynomial fitting of our aerodynamic. Okay, happy, but I don't understand the scope of this. Okay, see to the phase 2. What is the other phase of this? Is the following. If you have second phase, if you have this structure, what happens in the time domain? And you go back to the time domain. If you assume this polynomial structure and you go back to the time domain, the unsteady aerodynamics is described by time derivative of the state. Again, by time derivative of the state only. And therefore, you should have a pure differential system in time. And this is an advantage. No integral differential, only differential, but of higher order of differentiation. So you have new state in the systemistic point of view, new state, but finite state, not infinite, because when you have a delay, when you have an integral differential equation, you have theoretically an infinite number of states of your system, because you have a long theoretical infinite memory in your shoulder. Okay? This is very interesting. So we may approximate our state aerodynamic with a finite state aerodynamic with a higher order of differentiation, fitting the fact that we have an infinite memory in our system. And that's all. Stop here. See you next week. Ta-da! Mystery. Okay. Okay. And this is the mean, this is the strategy. This is the main strategy for describing the aeroelasticity, in the state space form only, and therefore do the control, because any controller guy needs to describe the system in this form. Typically, he doesn't care about memory. No. I want a finite state system, please, for performing my capability to design a controller. And this is the motivation of this kind of approach. This is a modern concept. For modern, I mean 10, 20 years ago. Okay? And thank you. See you next week. There is a question. Thank you too.